Hello, everyone. This section is on finding removable discontinuities, vertical asymptotes, horizontal asymptotes, and oblique asymptotes. It's a packet that we're doing outside of the book. The book, in my opinion, does a disservice, I guess, to the topic. I'd like to try and think I could improve upon it, so here goes. In the book section, they're going to talk to you about finding horizontal asymptotes, not very horizontal, and vertical asymptotes. This is the definition that they're going to give. When you have a numerator, you have a denominator, it's represented by some polynomials, and they're saying they have no common factors. And I'll talk more about that in a minute. I'll show you guys how to find vertical asymptotes, just like what this says. This is still true in the alternate method I'm going to show you, but there's a catch. Okay, it has to do with this statement right here that there are no common factors. The graph of f has at most one horizontal asymptote determined by comparing the degrees and being able to say what kind of asymptotes they have. All of this I think is rather cumbersome. What I'd like to do is to show you a different way of doing it that I think you're able to show a lot more understanding rather than right now you're just having to memorize this. I'm not usually a huge fan of memorizing stuff. I'd rather you understand it and can look at it and go, hey, there it is. I get it because it's right there. All right. Some notation that I'm going to use when I do this, and so you hear some of the words thrown out at you, is you're going to have a removable discontinuity, and that's going to be represented just by the initials RD. I'll explain what that is. It's a hole in the graph, and we'll work on that as we go. Literally, as if you had your graph and there was a hole in it. That's a removable discontinuity. You took a paper punch and punched a hole in it. We're going to have vertical asymptotes, and I'm going to write it as a combination of a V and an A. You're going to have horizontal asymptotes, and I'm going to write this as a combination of an H and an A. And then you're going to have oblique asymptotes, which I've been having some fun writing the symbol because I don't know if you guys recognize that symbol at all. It's the anarchy symbol. All right. I'm just combining an O with an A in it, and the only O and A that I knew was the anarchy symbol. So, you know, as long as we're going to be doing some of this drudgery of doing this topic, we might as well have a little bit of fun with it. Don't expect to go to another math class and have them understand that symbol. I invented it just for you guys, okay? So this is a hole. A vertical asymptote, it's a vertical line. You don't actually see it when you look at the graph, but it's there. Horizontal asymptote the same way. You don't actually see it. And in case you guys don't know the word oblique, oblique means that it runs at an angle, either in a positive direction or in a negative direction. And I'm using the slope to indicate whether it's positive or negative. Okay, the other way of doing this, you get away from all of this junk, is you have some function and you divide it by something. You're going to get a quotient, a remainder, written over your divisor. Here are some examples. Say you have this polynomial, and you could use synthetic division, divide it into this, and you would get this as an answer. What I need you to be able to understand and read out of this is your Q of X. It is your quotient. This is your remainder. And this is your divisor. Okay? You have to be able to read those pieces out. I'm truly not trying to be Captain Obvious here, but this, written this way, all your asymptotes and any holes will just jump straight out of it. You don't have to memorize any of this. Okay, sure, you have to memorize where to look, but I'm really hoping this is going to reinforce the skill. It'll also help you, in my opinion, for what comes fourth quarter when we start taking limits. And I've been talking to you guys already this year about this idea of taking a limit. Okay, so let me clear that out and go to the next one. If you divide this one into that, you're going to get 5 plus blah, blah, blah. This is your Q of X. It is your quotient. If you guys were to do this division symbol, it's what would be up here. And the 1 is the remainder, so it's your R of X. And this down here is your D of X. It's your divisor. Okay? Because this has a, so I'll give this away, because this has a variable, q of x. If you guys were to graph y is equal to x plus 3, forget this. Aren't you going to get a line that runs like this? Yeah, you are. Absolutely. This is going to create your oblique asymptote. This is what this is going to do. This is what this is. Oh my goodness. That's what that's going to create, is your oblique asymptote. Okay. This piece here, just like the direction set here, the zeros of this are going to create your vertical asymptotes. So that's where you look for your vertical asymptotes. In this one, it doesn't have a variable. If you were to graph y is equal to 5, you're going to get a horizontal line. So in this graph, you don't get an oblique asymptote because it doesn't have a variable. If you graph y is equal to 5, you're going to get a horizontal line. Okay? This is still q of x. This is still q of x. But because this q of x has a variable, it creates an oblique asymptote. Because this q of x does not have a variable, it creates a horizontal asymptote. This still creates your vertical asymptotes. And it's the zeros of it that create the vertical. So x equals -3 is going to be your vertical asymptote. You just set this thing equal to 0. That's all you do. Okay? All right. So let's look at a couple. Here is a polynomial. And I guess what I need to drive home here, you guys, in both these previous examples, is the degree of the numerator was bigger than the degree of the denominator. Okay? The degree of the numerator is bigger than the degree of the denominator. This has a 2 in common. You factor out the 2, and you're left with 2x squared minus 9. And this factors into x plus 3x minus 3. It's that difference of square pattern. And what I want you guys to see is that this cancels out. That creates a whole. When you have factors that cancel, you get a removable discontinuity. All right? That gives you this, because that's what's left. Distribute the 2 in. Here you go. This is not an oblique asymptote. This is a line. If you were to graph y is equal to 2x minus 6, you would see a line. There it is. But when you look at the table, look and see what's happening at -3. I entered this original equation in, and if you guys want, you can pause this thing, type it in your calculator, and you'll see exactly what I'm seeing here. This graph, entered just as I see it, creates a line, but at -3, down here it looks like, there would be a hole in the graph. Sorry, I don't have it on the picture. Okay? There would be a hole. You couldn't see it. It will never, these holes you'll never be able to see on the graph. They will always be invisible. But when you look at your table, you'll be able to see them. They will never show up on the graph, but they'll always show up on the table. Okay? So this is a line with a hole. Okay? It's a line with a hole in it. Because something canceled, the degree of the numerator was bigger, so you just ended up with this. If it was the other way around, if you flipped it, if you had x plus 3 over 2x squared minus 18, when stuff canceled out, you'd have 1 over 2x minus 6. This isn't a line, but it still has a hole because this thing cancels out. It's called a removable discontinuity. A discontinuity means that technically I can't draw this without picking up my pen, my pencil. Okay, a discontinuity. It's discontinuous. It is not continuous because there's a hole in it. Okay, the degree of the numerator is larger than the denominator. You get a line with a hole if you have a piece that cancels out. Okay. Now, what does this do to this f of x over d of x equals q of x plus r of x over g of x? Well, if this divides into this evenly, because that's what it would do. If you want, we can do it quick. 2, 0, negative 18, and I'm going to fill in negative 3. Drop the 2. That would be negative 6, 18. Look at your remainder. 0. Okay? When your remainder is 0, when this is 0, you do not have any asymptotes. None. Okay? And I can go back to the first page and show it to you, where these things have no common factors. That's essentially what just happened. You had a common factor. The sucker canceled out. Okay? Because you had a common factor, boop, and it turned into this, you don't have any asymptotes because all that was created was a hole in the graph. A paper punch punched a hole in the graph. It didn't create any asymptotes by this happening. So when r of x is not equal to 0, then what I said on the first page is true. This is going to be either a oblique asymptote or a horizontal asymptote. Sorry, that's such poor writing. It's not much better. Okay, either an oblique asymptote or a horizontal asymptote. And this is always going to give you your vertical asymptote, assuming your remainder is not 0. Okay. So what if your remainder is 0? Now I've done the work for you, I've done the division. If you type this in your calculator just as it is, this is what you'll see. There's no holes, nothing canceled out, there's no removable discontinuity. Okay? Notice the degree of the numerator is still bigger than the denominator. This is still true. If something cancels, you get a line with a hole in it. If something doesn't cancel, this is what you're going to get. This is going to be an oblique asymptote, and this is going to create a vertical asymptote. This one, I've changed the numbers around. This is what it gives you, but this time it's subtraction here. And you don't need to memorize this. There's no memorization of this needed at all. What you need to do is remember that this is your q of x. If you were to graph y is equal to x plus 3, 1, 2, 3, your slope is 1, this is what you would get. You would get this line. This is the oblique asymptote. Same thing here. 1, 2, 3. This is your oblique asymptote. Okay? And it creates two different graphs depending on how it appears. It's nothing you need to memorize. All you have to do is do the division. If you have a variable in your q of x, that creates an oblique asymptote. It created an oblique asymptote. If you don't have a variable there, then you don't have an oblique asymptote. You would have y is equal to 3 in the scribbled out case. That's a horizontal line. That's something you guys got to memorize, is that if it just has the y, it's a horizontal line. We've been working on that in Algebra 1 and Algebra 2. Okay? All right, so if the degree of the numerator is bigger than the denominator, one of two things is going to happen. Either when you factor it, something will cancel out, in which case you just get a line with a hole in it. If stuff doesn't cancel out, you do the division. This is your q of x. It's got, sorry, I'm hesitating here. It's got a variable in it, so this is an oblique asymptote. This is your vertical asymptote, so equal to 0. And we'll do some of the examples here. Okay? So here you go. This is what you're going to be given. The very first step is to factor it. So let me just practice factor. Not practicing, I'm going to write it up here. In case I screwed up, I got to erase. I'm not erasing down there. The leading coefficient is 1. It multiplies 2, adds to 3. So x plus 2, x plus 1. So this is the factored form. The simplified form is this thing's going to cancel out and leave you x plus 2. Notice there's nothing to divide by. So what that means is, and I can prove it to you here by doing synthetic division, negative 1, 1, 3, 2. My remainder is going to be 0. I know that already because this canceled out. So just let me prove it. I'm dividing this into that. So that would be negative 1, 2, negative 2, 0. So when you write this after something is canceled out, it means your remainder is 0. So it would be x plus 2 plus 0 over x plus 1. Now you may ask, do I really need to write it? Well, I'm just trying to illustrate the point and drive it home, that that's what this division process is. Okay? Now, yes, you have a removable discontinuity. A removable discontinuity is a coordinate. It's a place on the graph where there's a hole. I want to know, where is that hole? Well, you set what canceled equal to 0 and solve it. So -1 is the x value of your hole. Now, if you fill -1 back into the original, it's going to make this piece 0, which is going to make the whole top 0. -1 squared is 1, minus 3, plus 2. The top is 0, the bottom is 0. You get 0 over 0. That's called the indeterminate form. It means it doesn't tell you jack. Okay? There's no information to be gotten from this. But if you kind of wink and a nod and look the other way and fill this in to the simplified form, oops, I was going to write 3. Oops, a daisy. My arithmetic just isn't working so well here. You get 1. That's the coordinate of the hole. And if you type this into your calculator and look at your table, you could see that it's converging to 1. And we'll talk more about that fourth quarter, that it's converging to it. Okay? But what you need to get out of it right now is you fill it into what's left, and it will tell you what number to write there. Okay? Because it's a line with a hole, okay, there aren't going to be any asymptotes of any kind. You do have an x-intercept and a y-intercept, and we can look at those, assuming they aren't the hole, which they're not, looking at the coordinate. You guys need to remember that when you have an x-intercept, whatever your graph is doing, at that coordinate, your y is 0. Well, oops, I didn't mean to hit that button. Whoops. This thing is set equal to 0. Cross multiply. Whoa, oh, you shouldn't do it. You should use your simplified form. Pardon me. Excuse me, use your simplified form. I got sidetracked with the thing where I hit the wrong button. X equals -2. That's going to be your x-intercept. Go back to this. You set this thing equal to 0 because your y value would be 0. You could do it here, okay? Cross multiply, 0 equals x squared plus 3x plus 2. But remember, this thing factored into x plus 2, x plus 1. If you solve this now, you're going to get -2 and -1. But this isn't an x-intercept because it was your removable discontinuity. So this isn't an intercept. That's why it's better to do it in the simplified form, so you don't mistakenly label a removable discontinuity as an intercept. It's better to use the simplified form. So x-intercept, simplified form. Y-intercept. X is 0. It doesn't matter where you do it. If you do it here, you get 2. If you do it here, you get 2. So y-intercept isn't as picky. Okay? Now, you guys have a line that's got a hole in it. Domain. Can you go as far left as you want? Yeah, as far right as you want. Yeah. Do you have any holes or gaps in the middle? Yep, you got a hole. The hole is where x is -1, so x cannot be -1. Range. Can you go as high as you want? Yes. As low as you want? Yes. But do you have any holes or gaps? Yep, you sure do. You've got a hole. What can't the y value be? The y can't be 1. Okay. Let's try this one. Factored form. So that would be x minus 3x plus 2 over x plus 1. Nothing cancels out, so that's what you got. Simplified form, there isn't one because nothing cancels. So now it says divide the sucker. So -1, 1, -1, -6, 1, -1, -2, 2, -4. So you've got x minus 2 minus 4 over x plus 1. You don't have a hole because nothing cancels. Your d of x is always going to be set equal to 0 unless your remainder is 0, or I guess I erased it accidentally over here. Yeah, so that was x plus 2 plus 0 over x plus 1. Your remainder was 0, so you didn't have any asymptotes of any kind. Here, your remainder is non-zero, so you set your denominator equal to 0, and that gives you the equation for your vertical asymptote. You look at q of x. Q of x is either going to give you your horizontal asymptote or it's going to give you your oblique asymptote. It has a, if you were to graph y is equal to x minus 2, you're going to get an oblique line, not a horizontal line. So y is equal to, and I want the equations here, folks. I don't want you guys just getting sloppy on me and writing x minus 2. That's not the equation of a line, okay? Excuse me. Getting crabby with you and I start coughing. All right. What are you going to do quick? Hold on. Apologize for the inconvenience. All right. X-intercept. I said before back over here, it's better to do it with the simplified form. But this didn't have a simplified form. Okay. So go back to the factored form. Set it equal to 0. Cross multiply. And you get, sorry to cram it in the corner, x minus 3 x plus 2 equals 0. And you guys have done enough of these. It's a zero product property. 3 and negative 2 are going to make that 0. 3 and negative 2. Do not put parentheses around it. You guys, look. 3 is over here. Negative 2 is over here. If you put a parenthesis around it, you told me your x-intercepts now are 3, negative 2. Right there. No. If you put parentheses around, that's what you told me the x-intercepts are. It's not. So you guys have to understand, a list of numbers versus a coordinate. It's just a list of numbers. No parentheses. All right, y-intercept. Let x be 0. X equals 0. Y equals 0. Okay. Negative 6. Domain. All right. This requires that you guys graph the sucker. If you were to graph this, you're going to get a vertical asymptote at negative 1. You have an oblique asymptote here. Okay? Now, your graph has one of two choices. It's either going to come along here, in here, and how are you going to know what it is? You slap it in your calculator and you find out. Or it's going to come along in here and in here. Your graph's not going to cross the asymptotes. So those are the combinations that you have. And if you look back to this previous, whoops, went too far. And here, that's the two options I just drew for you. But notice how I did it is I put the vertical asymptote in, I put the oblique asymptote in, and that gave me the boundaries of where the sucker lives. Now, whether you're going to use the green one or whether you're going to use the blue one, domain. Can you go as far left as you want? Yeah. Can you go as far right as you want? Absolutely. Do you have any holes? No, because you didn't have any removable discontinuities or gaps in the middle. Yes, you have a gap. Where does the gap occur? At negative 1. So your domain is x cannot be negative 1. Now, if it's the green one, and let me go back here to look at this picture. Can you go as high as you want? Yeah. Can you go as low as you want? Yeah. Okay. Do you have any holes or gaps in the middle? As you go up to down? No, you don't. This one, can you go as high as you want? Yes. Can you go as low as you want? Yes. Do you have any holes or gaps? Yes, I got this big old gap in here. How do I possibly figure out what that is? Well, see, that's one of the problems that's created when we have oblique asymptotes. So, to make it easy on you guys, whenever you have an oblique asymptote, we're going to take the easy way out and just not talk about the range. If that's bothering you too much, if that's not very mathematical for you, I understand. I'm just trying to cut my losses in I'm trying to improve upon what the book has done for you, knowing full well it leads into a couple different conundrums. I think that the ability to get all the rest of this information is outweighed by, once we get here, we're going to go, you know what, we're just going to hold off on that. Okay? So I'm comfortable with this. To recap, first thing you do is factor and see if anything cancels. If something cancels, then write it in. If you want, as soon as something cancels, set what canceled equal to 0 and solve. That gave you the x value of the whole. If when you factor it, nothing simplifies, this is as good as it gets, then you do not have any wholes. If the degree of the numerator is bigger than the denominator, which all the ones in your homework tonight will, then you're going to have one of two things. You're either going to have a line with a hole, whoops, it looks like line with a hole in it, or you're going to have an oblique asymptote and a vertical asymptote. Okay? You read these from your Q of X, from this part right here. Whoops, sorry, these two. I circled the wrong ones. Well, let me clear that up a little bit. Okay, this is read from your D of X, set equal to 0. These are read from your Q of X. X-intercept, you let y equal to 0. In other words, you set this thing equal to 0, assuming you do not have a simplified form. If you do have a simplified form, then you're setting this equal to 0. Y-intercept, let x equal to 0. Domain, it's what I've been telling you guys all along. Can you go as far left as you want? Can you go as far... I think I drew it the wrong way. Can you go as far left as you want? Can you go as far right as you want? Do you have any holes or gaps? Gaps would be a vertical asymptote. Okay? If it has an oblique, we're not talking about range. If we are, look back at your y value of your hole to get your range. And if you have any vertical asymptotes, which tonight you won't. You won't have any holes and vertical asymptotes. In future assignments, in the next couple days, you will. Domain, you're going to look at the x value of your hole. Okay? Domain here is actually going to be created by a combination of two things. It's going to be your vertical asymptote. That's what's going to create the holes tonight, or the gaps tonight. But in future nights, it will be also the x value of your hole. Okay? All right, the y value. Okay, I probably should just be quiet and talk about it in future nights, because I think I'm just going to traumatize you guys. There you go. Okay, so that should be the end of tonight's. All right, 28 minutes.